Alrighty, well, we're going to get started. Got a pretty packed presentation today, so welcome everybody to another great green energy series. Today's green energy series, we talk about dual fuel heat pumps and particularly some considerations and features of dual fuel heat pumps that may not be very evident. So we'll get into it. So this presentation is delivered by Solar Oregon. Solar Oregon is a Oregon nonprofit that's uh, this year is turning 46. Solar Oregon was founded in 1979. We do lots of education, outreach, and community advocacy around solar. Um, some of the ways we do that education outreach is through webinars and then also in-person presentations. Solar Oregon does like how to go solar plus storage webinars, and they are also sometimes delivered in person at different venues such as libraries and community centers. Um, we have a annual Go Zero tour where a handful of houses that have gone solar are on tour. My tiny house, the off-grid tiny house project, was on a Go Zero tour a few years ago. Um, and every year we try to find some very interesting um, houses to put onto the Go Zero Energy tour. That typically happens sometime in um, the early fall. Um, we also do solarized campaigns where we bring together um, groups of homes in a neighborhood to go solar at the same time, and that results in pretty significant savings in the cost of going solar. And the reason for that is that more panels can be purchased in bulk. So then the cost per panel is lower, and then also really reduces the outreach cost for the solar contractor. Um, for most solar contractors, finding customers in particularly a down period is a significant cost to their business. And so when Solar Oregon does a solarized campaign and brings a handful of customers all concentrated in kind of one area together, that's a huge help to a solar contractor, and then they'll then be able to translate those savings into uh, reduced cost solarizing each home. We also do many peer-to-peer education events, such as this Green Energy series. Um, and another event that we do annually is a solar winery tour. The picture on the right is from a past year solar winery tour where the uh, the farm has actually installed bifacial solar panels, and these are semi-transparent solar panels that still let some light through. Um, and so if you plant in the shade underneath the solar panel, the plants actually still get enough light to be happy, but the shade actually reduces the amount of water that plant needs. And so a significant amount of water savings is possible. And of course, in a farm, you're not always producing every throughout the year. So, um, installing solar on a farm it actually helps the farmer have an additional revenue stream, and so that can be a major help for farms that are, most farms are not making tons of money. I mean, they're typically, pretty tight on their margins. So having this additional revenue of like being able to sell electricity is a huge help. And so each year we have on the solar winery tour a visit to farms that either have solar on sites for agrivoltaics or solar on their buildings, or they're involved in solar in some other way. So really exciting to see, how that pairing of solar and um, the winemaking business has really taken off here in Oregon. And so we feature several different wineries each year on our solar wine tour. This year's solar winery tour is on May 10th. You can check out emails or visit Solar Oregon's Eventbrite page to look for that event and sign up. So for all those things that Solar Oregon does, we only have two really hardworking staff. Everyone else, including myself, is a volunteer. And so if you like the work that we're producing, feel free to visit this link or the Solar Oregon website to donate a little bit of money to help our cause. And you're encouraged to use the features on Zoom to ask questions. I will keep an eye out for those questions and answer them uh, as many questions as possible. And so my name is Edward Louie. So during the week, I work at Pacific Northwest National Laboratory as a building energy efficiency research engineer. It's quite a mouthful. Um, Outside of work, I enjoy studying solar and high performance buildings and heat pumps and uh, everything kind of related to those kind of areas. You can find me frequently posting on LinkedIn. You can continue to see my tiny house, off-grid tiny house project. You may see some posts on LinkedIn about that. Um, so that's about me. A disclaimer is that this presentation does not necessarily reflect the position of Pacific Northwest National Laboratory, U.S. Department of Energy, or Solar Oregon, and I've made best effort to convey facts and information accurately. However, you're encouraged to do your own research and your own calculation before making investment decisions. So let's dive into this presentation about dual fuel um, heat pumps. We're going to look into kind of what is it, and then I'm going to spend quite a bit of time talking about comfort and the relationship between comfort and equipment runtime and matching uh, the heating output to the heating load of the house. So a concept called load matching and how that relates to comfort. So we're going to spend quite a bit of time on that. Then we're going to look at some numbers on the upfront cost of a dual fuel system versus a heat pump only system versus a air conditioner uh, only system with a furnace and kind of look into all those different scenarios. Then we're going to also look at the fuel cost or operating cost of heating your house with natural gas versus heating your house with electricity through a heat pump. Then we're going to talk about some uh, carbon emissions related to heating your house with natural gas versus electricity. Um, and then we're going to talk a little bit about installation complexity. And then if you do have a system that can choose and switch between heating with natural gas versus heating with electricity via a heat pump, um, then when does the system choose to heat your house with, gas versus electricity via a heat pump? Like, what's the control method? So there's different control methods, some that are basic and some that are very advanced. And we'll talk about that. And then we're going to spend some time on the conclusion slide, kind of really going over an overview of the pros and cons. So with that said, um, what is a dual fuel system? It is, as I said before, a system that has the option to heat your home with electricity via heat pump, and it can also switch to heating your house with either natural gas or propane. Um, what's kind of unique about a dual fuel system is kind of how the in how these different components, in order to make that possible, stack up in the air handler. So, a dual fuel heat pump system is one where you have a traditional gas furnace, which consists of typically a blower at the bottom and then a heat exchanger, where the natural gas or propane combustion happens to be able to produce heat. And then you have a coil sitting on top of it, and this coil is connected to an outdoor unit that has a reversing valve, and that reversing valve allows this coil to operate in cooling mode or air conditioning mode during the summertime, and then it can also operate in heating mode in the wintertime. And so uh, at any point in time, the system only operates in heat pump mode or gas mode. You cannot have both of them running at the same time. You can imagine how problematic that would be. You would have a very hot air being produced by this uh, gas heat exchanger, and then that super hot air would then make it cook the coil so hot that the refrigerant in the coil would not work properly. And so there's controls in a dual fuel heat pump so that you can never operate both at the same time. Now, the in a heat pump only air handler, the components are fewer, and in addition to that, the typically in a heat pump only um, cabinet, the blower is on top of the coil, um, and the reason for that is you gain a little bit extra efficiency um, by having the blower on top of the coil so that it's a pull-through air situation. Um, the reason why that the blower can be at the bottom and the coil on top in a gas furnace situation is because this heat exchanger for the gas um, heat exchanger helps kind of diffuse the air from the blower so that by the time it hits this coil, it's also nice and even so that there's even airflow across the coil. But when there's no gas heat exchanger and it's just a refrigerant heat exchanger, then a pull-through system allows for more even air to go across that refrigerant coil. So that's why the positioning is a little bit different. Now, um, a concept that we're going to talk about is comfort, and comfort's really important in a heating cooling system because it's really the main reason why we have a heating cooling system. Because honestly, like we don't really need to heat and cool our homes beyond like keeping the pipes from freezing. Um, if you wanted to in the wintertime, you could wear like really thick socks and really thick pants and gloves and a jacket indoors and be fine. Nobody really wants to live like that, so that's why we have heating systems to remain comfortable. But comfort is not just the air temperature, it's also the temperature of the floor, the exterior walls, the temperature of our furniture, all these things, the temperature of these surfaces and objects affect our perception of comfort. And that's because the human body is always radiating heat. Um, but how fast we radiate this heat depends on how cold the surfaces around us are. So if the surfaces are colder, then we'll be radiating heat away from our body faster and therefore feel colder. Similarly, those surfaces, the temperature of those surfaces is also radiating heat towards us. And so, like on a sunny day, it could be 70 degrees and sunny, but since we have that radiant energy from the sun directly against our skin, it feels warm. But on a cloudy day, even if it's 70, it feels cooler because we're missing that radiant heat. So the mean radiant temperature, or the average temperature of all these indoor surfaces, matters a lot. And the temperature of these indoor surfaces are large, greatly affected by the how long the air handler runs. Um, so you can imagine that like the thermostat is sitting maybe in your hallway, and the walls in your bedroom could cool off quite a bit. And if you're in your bedroom, then you'd be feeling those cooler wall surfaces. Um, but it takes quite a while for that thermostat to then realize that, hey, like we've cooled off not only the wall surfaces, we've then finally cooled off the interior air temperature enough to then get the heating system to turn back on. So if the heating system could run for many minutes out of the hour or a high percentage of the time, then those wall surfaces are continuously getting a stream of heat to keep it warm, and so then um, you in the bedroom will then be more comfortable. So this is a very important concept, and I alluded to the idea of runtime being a link to this comfort. And um, one thing to note is that a dual fuel system will generally give you a higher degree of comfort. And the reason is because a dual fuel system typically has a heat pump that has a significantly lower heat output than the gas furnace. Um, that's not a bad thing. Um, Oftentimes, the gas furnace is quite oversized for the home's heating load, or the amount of heat it takes to keep that home comfortable. And the reason why many gas furnaces are oversized is, well, one is tradition. The homes in the past used to be much leakier, much more poorly insulated than homes of today. And so gas furnaces back then were manufactured and sized for those very leaky homes. Um, but the other thing is sort of just the nature of burning a combustion fuel source. It's a higher energy density process. It generates a much higher temperature flame, a much higher temperature air, and so that's also one of the reasons why gas furnaces have higher outputs. And some of the some of the smallest gas furnaces you can find on the market are around 40,000 to 60,000 BTUs in output. So that's pretty large. I mean, some of the largest heat pumps you can find on the market are 60,000 BTUs. So if some of the smallest gas furnace you can find are start at 60,000 BTUs, so you can see where the discrepancy is. But on a mild day, your home does not need 40,000 or 60,000 BTUs to stay comfortable. It needs far less heat output from the heating system to stay comfortable. So having a um, heat pump that can run on those mild days and produce, like for example, 24,000 BTUs, that output is, much closer in matching to the heat loss of the building on a mild day than the 40 or 60,000 BTU gas furnace. And so that translates to then longer run times, and then there therefore has more minutes out of the hour for the system to be blowing warm air on your exterior walls and onto your floor, your ceiling, and furniture to keep all those interior surfaces warm, and that results in um, greater comforts. So, um, on a mild day, sometimes even the 24,000 BTUs for example, a 2 ton heat pump, that's still too much. Um, a modulating heat pump or an inverter driven heat pump can modulate its outputs quite a bit. So, like in this example, this 2.5 ton heat pump over here shown on the right hand data, it might have a nominal output of 2.5 tons, but it can modulate down to an output at 47 degrees, can modulate down to only 9,200 BTUs. So, a really low amount of heat, so that, on a mild day when it's sunny and you get that additional heat gain through your windows, um, your house might only need a tiny bit of heat output in order to stay comfortable. And so um, a modulating or inverter driven heat pump can do that and then result in the long run times to, again, keep those interior surfaces warm. And that large modulation is much greater than the modulating range of even modulating furnaces or two-stage furnaces. Because, as I said, like the smallest furnaces you can get are out on the market are around 40,000 or even 60,000 BTUs. And so then the question remains like, well, if you're saying that, a lower output to match the heating needs of the building on a mild day is good for comfort, then wouldn't that be good enough to get a two-stage furnace or even a modulating furnace? And yeah, that might be okay. Um, but like a two-stage furnace, if it's 40,000 BTUs, the first stage, the low stage, is is still 28,000 BTUs. So, again, like if your home needs 10,000 BTUs on a mildly cold day, then, the two-stage furnace, even on the low output, is um, oversized by quite a bit. And so then you don't get the runtime needed to, you know, keep those exterior surfaces, continuously warmed in a low rate of outputs. Same thing with modulating furnaces. If 60,000 BTU modulating furnace might be able to only modulate down to 30,000 BTUs, which is still a lot of outputs um, for a home on a mild day. So the the conclusion from this slide is that heat modulating heat pumps or inverter driven heat pumps have a much larger modulation range than the best multi-stage or modulating gas furnaces. So um, on a well, I keep mentioning the concept of a mild day, and that's because there are most of the winter consists of mild days. There are actually very few extreme days, um, and a climate like an extreme climate like Eastern Oregon or Montana or Nebraska, these places might have more extreme days, but they still actually have the same number of mild days in the swing season um, as a mild place like Portland, Oregon. And so um, even the places that experience very extreme wet, cold days have a lot of hours and a lot of days in the year when they could benefit from a heat pump that can produce, a low amount of heat that can match the load of the building on those very mild days. Um, so this graphic is an example from Portland, Oregon. Um, the blue columns show the what's called the load times the hours. So basically, we're talking about the number of hours in the year um, when the outdoor temperature is 50 degrees, for example, or the outdoor temperature is 40 degrees. And then those hours are then multiplied by, okay, well, what is the um, heating requirement to keep this home comfortable when it's 40 degrees outside. So that multiplication will result in those blue columns, and the for the most amount of comfort, the goal is that your heat pump can have a modulation range that covers the most of the blue area. Um, and there's not going to be a heat pump that can do it generally perfectly. So like for example, in the previous slide, I mentioned that, the example heat pump can modulate down as low as 9,000, maybe 10,000 BTUs. Well, if it's 55 or 58 degrees outside, um, this example home actually, the heat load is so low that it falls below the 9,000 BTUs needed. So then this heat pump will still, even a modulating or inverter driven heat pump can't modulate low enough to match the load. So it'll still turn on and off and cycle um, in the extremely mild days. Um, Now, for Portland, the design temperature, which is this vertical bar here, this represents, looking at a typical year, 99.6 percentage of the hours in the year are have a temperature warmer than this value here. And as you can see, that makes sense. Like there's barely a blip of the blue bar to the left of this vertical line here. And so um, if you want to have a heating system cover like 99.6% of the times in a year so that you're comfortable, then you want the heat pump to be able to have the heat pump data shade um, such that like we'll look at like the next slide here. You can see here that uh, you have a lot of the blue bars um, that are in the area that's where the heating demand is exceeding the output that's capable of the heat pump. And so, versus in this slide here, there's almost no bars, um, which is the load of the home that's in this purple area here where supplemental heat is needed. So, in a mild place like Portland, Oregon, if you pick the right heat pump, there's basically no scenario where no day out of the year where it gets cold enough that a heat pump can't keep up. Um, and that's why it's important to, define how cold is cold and really look at the extremes in the city that you're located in. So, this example here is in Burns, Oregon, and Burns gets significantly colder than the cities that are west of the Willamette Valley. They actually get days when it's, you know, minus Fahrenheits, so very, very cold. And so you can see here that there's a significant number of these blue bars that fall in that range that that are in this purple area. And so then this would be a location where a dual fuel heat pump would have greater benefits because then during these hours, the heat pump the can is not able to keep up, and so then a dual fuel heat pump with that much higher output could then come online and be able to keep the house comfortable when it's 5 or 10 degrees outside. Now, you could in Burns, Oregon, actually then pick a heat pump that is able to meet more of these hours because there's actually hundreds, if not thousands, of heat pumps on the market that can produce 100% of the rated heat outputs down to 5 Fahrenheit. And the design temperature in Burns, Oregon is 4. So if we pick the larger heat pump, it will then the maximum outputs of the heat pump, which is in this really dark red line, and the minimum outputs of the heat pump, these lines will actually then shift up, and then as a result, then what would happen is that this graph it'll look like a greater percentage of these blue bars here on the left end of the graph will be able to be met by the heat pump. Now, the downside of picking out a larger heat pump is that then you would probably have a larger number of hours in the year in this green area where the heat pump would cycle on and off because it can't modulate low enough. So it's when you have, more extreme extremes, it becomes harder for, one heat pump to be able to meet both the extremely mild days and then also the extremely cold days. So a compromise could be that, dual fuel is the right compromise so that you can size a heat pump so that it's not so big, so that you still cover, so that there's still very few hours and few days where the heat pump needs to modulate and I'm sorry, cycle on and off because the load is so low. But then you still have a large enough furnace to be able to cover when it ever gets to be minus 10 or minus 20 degrees outside. So, um, yeah, location makes a major is a major deciding factor of whether to go dual fuel or just straight heat pump only. Now, upfront cost, there's actually not a significant uh, difference in price between a system that has a heat pump with a furnace, and we're talking about typically a system with a heat pump and a furnace would have a relatively cheap and a simplistic heat pump and then a relatively cheap and simplistic furnace. So, the cost of two cheap components together equals roughly the cost of one very advanced cold climate heat pump that has the ability to have the inverter so that it can modulate to a very low levels of heat output on a mild day. But then that inverter can really speed up the the speed of the compressor so that you can maintain heating output on a very cold day. Um, it, of course, like if you go with the cheapest this single stage heat pump and the cheapest gas furnace, you're saving roughly maybe $1,000 going with a dual fuel system versus a advanced heat pump that has the inverter. But I mean, there are some inverter heat pumps out on the market that are really, really inexpensive. Um, are they really good? I don't know. I've never installed one of these really cheap ones, but they are on the market. So in which case they're even cheaper than the cheapest dual fuel heat pump possible. And the cost I'm showing here are wholesale prices of just the main components. So like I'm like the furnace, the coil, and the outdoor units. And we're not talking about installed cost, okay? So there's no labor, no shipping, no cost of miscellaneous parts, no permit fees associated with these numbers. And this data is from February of 25. So if the recording gets watched a year or two in the future, these prices could change, a little bit or a lot. I don't know what the future economics will look like. Now, let's also look at the scenario of, well, what if I don't care about having dual fuel? A furnace is more than able to heat my house today. I'm just going to install a furnace, and maybe I don't care about the um, additional comfort of having a heat pump that can, produce, a half or a third of the output of the gas furnace. Um, I only care about upfront cost. How much will I actually save? Well, surprisingly, you're not saving that much money either. So there's the parts list to go with an air conditioner and a furnace system is not much different than a system that has a heat pump with a furnace. The difference between an air conditioner and a heat pump is, for the most part, a reversing valve, and that reversing valve um, in the outdoor unit costs maybe $20 or $30 at the factory. Um, so very small amount of additional cost. And then at the wholesale equipment cost, you're often talking about less than $100 in difference between getting a straight air conditioner versus a heat pump. Um, and another scenario to look at is in the bottom. So the question then in that scenario is, well, if my air conditioner dies, um, should I just get a new air conditioner or should I, get a heat pump? So in that scenario, the your furnace is still in good shape. Maybe it's not that old. Maybe you replaced it recently, but then now the air conditioner goes out. Um, Instead of replacing the coil and the air conditioner, and you replaced it with a coil with a heat pump, um, it's an additional like $500. So the conclusion from this is that, well, if you have a air conditioner plus furnace system, um, there's very little reason to not, if your air conditioner dies, go with at least a dual fuel system so that you can gain the comfort benefits of having a heat pump run on those mild days. Now, what about the cost? So we've mentioned that there's not a whole lot of cost difference on the upfront cost side, but what about operating costs? Like, is heating your house with gas versus heating with electricity via a heat pump, which is cheaper? Well, that's very tricky. It's perhaps one of the trickiest questions for an HVAC contractor to answer because there's a lot of factors at play. Um, but currently, here, at least in Portland, Oregon, where we have Pacific Power or Portland General Electric and then Northwest Natural, currently the fuel cost of natural gas and electricity is such that it's sort of a wash depending on factors. So, like, for example, if you currently have a 96% efficient gas furnace, um, then if you were to switch to a heat pump that has an average efficiency of 3.2 over the course of the winter, um, then and the cost of electricity is 19 cents, then switching from a 96% efficient natural gas furnace to a heat pump with a efficiency of COP of 3.2 at a electricity cost of 19 cents, and if your current gas cost is $1.68 a therm, you would save $3. So basically no cost difference. Um, Now, if your current gas furnace is less efficient at 80% efficiency, um, and you switch to a heat pump with a COP of 3.2, you would save $100. So still not a lot of savings. Um, but if electricity went up 1 penny to 20 cents a kilowatt hour, and gas prices remained the same, then and you had a 96% efficient gas furnace, you go switching to a heat pump, you would end up costing you about $29 more per year to heat your house, which is again a pretty trivial cost difference. Um, but of course, nobody really knows what the future costs of natural gas or propane or electricity is. So, these calculations could actually widen in the future, or they can remain in this scenario. Nobody really knows. Now, what is a little bit more, quite a bit more certain, is the environmental um, benefits of a heat pump. So basically, everywhere in the US, it's less carbon emissions to run a heat pump than a gas furnace. And the reason is that 1 therm of natural gas produces about 12 pounds of CO2, and uh, here in Portland General Electric land, the same amount of energy via electricity will be 20.7 pounds of CO2. But if you had a heat pump with a coefficient of performance of 1.6, you would be carbon parity with natural gas. And gosh, there's almost no heat pump that is that crappy that gets a coefficient of performance of 1.6. You could typically get a coefficient of performance of two-ish, 2.5. Um, Even the worst heat pumps on the market, poorly maintained, kind of old, you can get a coefficient of performance around like 2.5. And modern heat pumps could easily get a coefficient of performance of 3. And so then in that case, then you're well into heating with electricity via a heat pump being less carbon. Um, in the example scenario where you have a 96% efficient uh, gas furnace, if your heat pump has a COP of 3.2, um, you're going to be saving about 1 ton of carbon per year. Um, there's a really good paper that looks at this on more of on a macro scale across the U.S. It's by Ian Walker and some of his colleagues at Lawrence Berkeley National Lab. There's some of the details. You can Google that paper and read it for yourself. Very fascinating paper. On the install cost side, having a dual fuel heat pump likely will result in some higher cost of installation, and that's because the installer needs to not only install the heat pump side, they also need to install the gas stuff, which would entail calibrating the gas valve in the gas furnace based on the gas pressure from the gas meter. And then, of course, when all the gas connections need to be checked for leaks. The combustion of natural gas needs to be vented to the outside, and so then there needs to be a test of the ventilation or the vent of the gas system, and so then time and resources need to be expended to do those types of tests. Um, a very efficient gas furnace, like 95, 96, 97% efficient gas furnace, they produce condensate, and that condensate's a little bit acidic, and so then you need an acid neutralizing filter in order to protect the sewer pipe or the condensate pump from being corroded by this slightly acidic condensate. So then that's a cost, and then also it's an ongoing maintenance to restock that neutralizing filter material. And then, of course, If you have natural gas in your house, you should have a carbon monoxide alarm. And increasingly, it behoove you to, if there's the cost difference is not very much, to get a dual sensor, both carbon monoxide alarm and a natural gas leakage alarm. And so one detects a carbon monoxide will kill you slowly, and then a gas leak will cause potentially an explosion in your house and kill you quickly. And if you have an alarm, it behooves you to get one that can detect and alarm you to either scenarios. Um, so if you have an all electric home, then you don't need that, and then the installer doesn't need to do all these additional steps. Now, let's get into control methods. So, if you have a system that has the option to heat with gas versus heat with electricity via heat pump, then the thermostat needs to decide when to switch from one to the other. Um, the first two bullets are the common ways that this switching occurs. One is to just define a fixed temperature to switch over. That's not a very good method because let's say like on calculation the heat pump can keep up to like 20 degrees outside, but there's different 20 degrees outside. Like it could be 20 degrees and 20 miles per hour blowing wind, or it could be 20 degrees and sunny outside. That those two scenarios results in very different heat loads on your house. And so that's why a fixed temperature switchover is not very good. The other common way to do it is to do something called droop. And how droop works is that let's say you set your thermostat to 72 and the heat pump is running and it's running and it's running, but then like the temperature of your house keeps dropping even though the heat pump is running. And so therefore the heat pump's not able to keep up. And that would be an indication that the outside conditions are so cold that the heat pump can't keep up to keep your house warm. And so droop is set up so that like let's say like if it's 72 and the house keeps dropping and then by the time it drops 2 degrees, for example, you set the droop to 2 degrees. Then when it hits 70 degrees, then you'll turn off the gas, I mean turn off the heat pump and start the gas furnace to then heat your house with the gas furnace. You can in the settings, and it's buried in the settings. It's typically a setting of the thermostat that an HVAC contractor would set for you, and generally, you as a homeowner, you would not want to try to find this setting in the thermostat. But you could set it to 4 degrees or something so that your house cools off even more before the gas furnace starts up. A really smart thermostat will be one that has the data for example, if your electricity is not the same cost all 24 hours, for example, if you have a time of use rate and that time of use rate happens to be like expensive electricity from 5 p.m. to 9 p.m., for example. Well, during that expensive electricity period, then it would be programmed into the thermostat. And then during that time, if the house needs to be heated, it would then use natural gas instead of electricity because maybe it's just not economical to heat with expensive electricity. Um, the environmental balance point is another way that a really smart thermostat could run the system. Like you may want to minimize your environmental footprint. And as I said in before that, if you have a COP above like 1.6 in at least Portland General Electric, um, uh, the carbon intensity of electricity of recent Portland General electricity mix, um, a COP of 1.6 would be carbon parity, but that's a annual average. And what really happens is the carbon intensity of the kilowatt hour of electricity changes all the time. It changes over the course of a day, and it changes over the course of the year. You can imagine that at noon, when there's sun, not only is that your neighbor's solar panels and maybe your solar panels, or the utility certainly has some solar panels. Those are all producing clean electricity, so the amount of uh, natural gas or coal power that needs to supplement in order to meet the load on the uh, electric grid is less, and so then you get cleaner electricity during the day. But then at midnight, when there's not a single solar panel producing any electricity, um, then uh, the electrical load has to be met by um, all coal or natural gas, or uh, in addition to hydro. But there'll be a higher mix of um, the carbon intense fuels, and so you would have dirtier electricity in the middle of the night. And then the same would apply from in the winter versus the summer. And so this different intensity, maybe in a location, the electricity at certain hours of the day is so uh, not clean that it may be actually cleaner to run and heat your house with natural gas instead of electricity. So a smart thermostat with this data could make that decision on your behalf to minimize your environmental impact. Um, the number of smart thermostats that can do this type of stuff is very limited. I only know of one produced by a company called BKR Energy. They're a Canadian company, and as far as I know, that thermostat has data for only a select number of utilities. And so, like, if you were to somehow procure that thermostat and put it in Oregon, um, that thermostat may not have data about Pacific Power or Portland General Electric's electric mix to be able to produce a graph data like this and make decisions. So it may not even work. But in the future, this is certainly possible. We have the capabilities today. We just need to kind of pull together that data, and then of course, then the electric utilities need to make this data available. Um, this data is from kind of a modeling, energy modeling data. So it's not necessarily real data from like February of this year, for example. I mean, it's roughly true, but if you want exact data, then the electric utility needs to produce it. This data is from what's called a Cambium data set from National Renewable Energy Lab, which is a really good data set. It's worth looking at, but the actual emissions can be different. So with that, let's kind of run into some conclusions. So dual fuel, um, it's a good option if you have very extreme cold uh, weather in your city. But if you live in, for example, west of the Cascade Mountains, um, there's probably not a location that gets cold enough that you really need that gas furnace backup. Um, but we still don't know what the future price of natural gas versus the future price of electricity is. So, maybe that fuel flexibility is enough to sway you to have that backup. But, it is extra cost to keep two accounts open. So, for all the times when the fuel is kind of like I was showing in the previous slide, um, it's basically a wash between heating with natural gas versus electricity via heat pump. Um, is it worth keeping two accounts open for the possibility that those pr fuel prices will then deviate and from each other in the future? I don't know. I can't answer that question for you. Um, there's also the concept of redundancy. The what if your gas furnace stops working? Well, then you can still be heating your house with a heat pump. And what if your heat pump stops working? Then you can keep heating your house with the gas furnace. But there's a cost associated with that redundancy, so you're willing to pay for it. And then what's the chance that, either system fails? Well, I guess it's pretty low if you maintain your equipment, keep your filters changed, every few years get a HVAC contractor to inspect the equipment to make sure it's working and as it should be. Um, and Still, though, in the Willamette Valley, you may find a conservative contractor that still, is very afraid that, you will be uncomfortable on the coldest day of the year and then complain and call them on the coldest day of the year when they really don't want to come out and like do anything. Um, And so, in order to reduce the customer complaint to zero, um, they would be unwilling to install a heat pump only system and try to push you towards a dual fuel system, even though, as I said, like in west of the Cascade Mountains, there may not be a location where that makes sense. But conservative contractors is something uh, if if you want to get more conservative contractors to install more heat pumps, then maybe a dual fuel is a good option. And of course, the main most important thing about dual fuel is that you have that additional comfort. You can still gain that additional comfort with a heat pump only system, but if you have a straight furnace system, you won't gain those greater comforts associated with the longer run times that you would with a dual fuel system. Um, you certainly use less natural gas, and for the most part, there's very few scenarios where it would be more pollution, so it's almost always less pollution. Um, and then in the few minutes out of the hour or few hours that a heat pump in winter goes into defrost, a heat pump only system would typically either blow some cold air or it will turn on an electric resistance auxiliary heat in order to keep the air warm during defrost. If you have a natural dual fuel system during defrost, the thermostat will actually then turn on the gas furnace so that you have heat during the defrost period, so that you won't need electric resistance auxiliary heat. Um, Not that you need auxiliary resistance heat in a straight heat pump system. If you're okay with, 5-10 minutes every hour or 2 or 3 hours, having either no heat or a slightly cool air coming out of your vents during the defrost period, then you really don't need electric resistance auxiliary heat. Um, some cons of a dual fuel system is, you have two systems to maintain. You need uh, that's more cost, and it's unnecessary backup for many climates. Um, Sometimes it's higher hardware cost, but as I said, like the higher hardware cost is usually a wash. Um, Certainly there is likely to be a higher install cost because of, the need to like pipe the vent the natural gas and pipe the natural gas and to test all the leaks and safeties associated with having gas. Um, and then there's a risk of carbon monoxide and gas leaks when you have gas in your house. Um, and the just thing about and then also with a dual fuel or system where you have a cheap heat pump, which therefore is typically a single stage, you potentially have less dehumidification than a variable speed heat pump. Um, but here in Oregon, it's not that big of a deal. We don't really have a humidity issue. This could become a big topic to really discuss if we were in, the American uh, Southeast where it's very humid, but we're not. And if your AC goes out, there's really no reason not to get a heat pump to replace that central AC. The cost delta is really small, and you gain a lot of comforts. Um, and so that's a really important point to I think take away from this presentation. And then I also want to tee up some upcoming events. So we see that, today was the Green Energy Series about dual fuel. We also have some coming up webinars about how to go solar plus storage. We also have a webinar coming up about comparing solar quotes. Um, the next Green Energy Series on April 5th is going to be about renewable energy policy in Oregon, and taking a look at some of the um, changes in place or on the docket or likely to take place, as the landscape of 2025 has quite a bit of volatility. We'll take a look at that. We're still trying to figure out who to bring on as a speaker. It may be me, it may be another Solar Oregon staff speaking on that, or it might be somebody we find that's even more qualified to speak on that topic. That's April 5th. And then at the beginning of the presentation, I mentioned the Solar wine tour. That's on May 10th. You can sign up and get your tickets today, and I encourage you to do so. It's a really quite an interesting tour. And of course, if you like wine, you get to sample and drink wine. Um, so that's all I have. And let me see if there are questions. There are questions. Okay. Um, all right. So there's a question about the Cambian NREL charts for carbon is different than Portland General Electric's time of day rates. So we're talking about this right here. So time of day rate is electricity prices. It does not have any electricity prices and carbon intensity are not related. Um, so uh, you're comparing apples to oranges. But even if Portland General Electric were to release the hourly emission intensity of the electricity, if that data was available, it may not look like this chart exactly. So one is modeling data, and the other one would be real data. Um, Another question is any pros and cons during power outage using generators? Um, yes. So if in a dual fuel system, let's go back to maybe one of the earlier slides to look at a dual fuel system. Uh, this the only components in a gas furnace that uses electricity is this blower, the control board, and maybe a tiny bit of electricity to light up the screen of the thermostat. So it's relatively little electricity to for a generator to support a gas furnace during a power outage. That's not the same compared to a heat pump, which, you need electricity to not only run the fan and the thermostat and the control board, but you also need to run that compressor and the relatively large fan outside on the outdoor unit in order to power all those components during a power outage. So this you would need a smaller generator to power a gas furnace during a power outage compared to powering a heat pump, or the generator would need to work less hard and therefore can run for more hours powering a gas furnace during a power outage compared to a heat pump. But in order to make that happen, though, you will need to uh, have either a transfer switch or a disconnect. One way that people do, instead of having a transfer switch in their electrical panel for a generator, what they do is they wire the furnace in with to a plug so that during a power outage they can unplug the furnace from that plug and then plug into an extension cord and then run the extension cord outside to the generator and power the furnace that way. Um, Whether that modification, instead of hardwiring the gas furnace and instead wiring it to a plug, whether that's legal from a electric code perspective or not, um, there's quite a bit of a debate about that. You could probably find an electrician be willing to do that for you, and so then you have that option. But if you don't have the ability to then like isolate the gas furnace, then even during a power outage, it could be really difficult to power a gas furnace during a power outage. And then another question is, are there tax credits for changing from AC to heat pump? Um, yes. Um, there are lots of tax credits or rebates for heat pumps. Um, Again, 2025 is kind of a volatile year, so what rebates are applicable at any point in time will vary. As far as I know, in Oregon, we have not changed the rebate landscape too much yet. Um, I don't know whether that will change, 3 or 6 months into down the road or next year. So if you're interested in heat pump tax credits or rebates, then maybe act quickly would be maybe my suggestion. Um, yeah, so that's my answer to that question. And Is there other questions or comments in the chat? Let's see. Q&A. That's good. And what about chat? Yeah, I'm having a hard time accessing that. Let's see. Maybe not. Okay, well, with that, then that concludes this Green Energy series. I hope you all have a great rest of your Saturday and look forward to you on a future event, whether it be the next Green Energy series or the wine tour or one of the solar plus storage webinars. And with that, everybody have a great rest of your Saturday, and we'll stop the recording and end this presentation.